In this video, we'll walk through basic steps to take when using SPSS to conduct a multiple linear regression analysis. Multiple linear regression allows us to estimate the unique effect of each predictor variable in the analysis while controlling for the unique effects of all the other predictor variables. In the case of a simple linear regression with just one predictor, we interpreted the beta coefficient that results as the change in the outcome given a one-unit change in the predictor. In multiple regression, we interpret each beta coefficient as the change in the outcome given a one-unit change in the associated predictor while holding all other variables constant. Let's use the example presented in the regression chapter in which we're interested in investigating the effect of music lessons on first graders' math test scores. In this example, we're interested in whether music lessons predict first graders' math test scores while holding constant other theoretically relevant background variables. We'll use the data file titled Miksza and Elpus, Music Lessons and Math Tests, with regression 2 in parentheses for this example. We'll conduct a hierarchical regression. First, we'll test the model with music lessons as a predictor and first grade math test scores as the outcome. Then we'll test the model with music lessons as a predictor and first grade math test scores as the outcome, but also include a set of other variables that may be important to consider when evaluating the relationship between music participation and academic achievement, namely students' urbanicity and socioeconomic status. Once we do that, we can then compare the first model to the second model to see if the second model is a significantly better fit to the data, or in other words, if the addition of the student background variables of urbanicity and SES result in more variation explained or any changes in the relationship between music participation and academic achievement. So we're going to go to the Analyze menu here under Regression into Linear Regression, and we're going to put Math Test Grade 1 into our dependent variable outcome, and then we have music participation as our independent variable. And now we're going to leave that as a first block. So in other words, first SPSS is going to run a simple linear regression. We're regressing math test on music participation. And we'll click Next, and we're going to add SES and urbanicity into the second block to fulfill the second step of our hierarchical linear regression analysis. So interestingly, urbanicity is a nominal variable with more than two categories, so we can't simply enter it in here. Instead, we have to use dummy variables that are created for you in the data editor here. So in other words, we have variables that have unique codes representing each of the various urbanicities. There are 4. And so you see if somebody is coded as urbanicity 2, they have a specific dummy variable saying, nope, 0, they're not in urbanicity 1. 1, yes, they are in urbanicity 2. Nope, 0, not in urbanicity 3. And nope, 0, not in urbanicity 4. So interestingly, we can only put in, as it explains in the chapter, 3 of the 4 dummy variables to avoid a true problem with multicollinearity. So we're going to put in urbanicity 2, 3, and 4, therefore making urbanicity 1, which happens to be urban setting, as our reference category. So the last thing we want to do here is ask for R-squared change statistics. So in other words, we want SPSS to also compare these two models, the model with only music participation and the model with these other background variables added to each other. And we can click OK. Yeah, and so here we have our summary. In Model 1, this variable was entered, and in Model 2, these variables were entered. The summary statistics for the overall variance explained and any change in variance explained from Model 1 to Model 2 are presented next. We see here that we have about 1% of the variance explained by music participation at all. Whereas when we add in SES and urbanicity, we have an additional 13% of variance explained now that we have a value of 0.14, roughly 13. In other words, we can look here in our column and see specifically SPSS has computed the R-squared change from Model 1 to Model 2, simply subtracting these two numbers to get 0.126, roughly 13% or 0.13. And then there's an F test here, a test that will actually compare whether this change, 0.12, is a significant change or not. And so we see our sig value for this change statistic test of which is well below the threshold of 0.05 for statistical significance. So we can say, yeah, there is a significant difference between Model 2 and Model 1 in the amount of variance explained. So then we have our model ANOVA for each of the models. Model 1, again, with just music participation, and Model 2 with music participation and several other background variables. And both of these models are saying that there's a non-zero amount of variation explained, whether you're just considering music participation or all of them together. And then we have our coefficients. With out-of-school music lessons in the equation alone, it looks like for students who do take lessons, in other words, those students who are coded as 1, you would predict on average an increase in math test scores of 4.25 points. For each unit increase in out-of-school music lessons, you could imagine an increase in math test scores, or predict an increase in math test scores of 4.25 points. Since this is a binary nominal variable of 0 and 1, there's only one unit to increase from 0 to 1. It's essentially switching back and forth between whether they didn't, or did have music lessons. And then we have our statistical test of that coefficient, and yes, that is, we can reject the null hypothesis that that coefficient would be 0. And then the standardized coefficient as well. So of interest then is what happens to that relationship when we add in these other predictor variables, socioeconomic status, and our suite of urbanicity dummy variables that represent the different urbanicity categories of suburb, town, and rural. And what we notice is that the effect of out-of-school music lessons on math test scores goes down pretty drastically, from an increase on average of 4.25 points on the math test to an increase on average of only 1.71 points on the math test if you're taking music lessons. And in fact, this is now small enough that we can't rule that to be statistically significant, given the standard error and the t-statistic that results. So on the other hand, we do find a significant effect of socioeconomic status and a significant effect of urbanicity with rural, the rural dummy variable indicating a less than 0.05 p-value. And then lastly, SPSS will tell you, well, you have variables that are input into the menus but weren't used in some models. And well, obviously in Model 1 we were only interested in out-of-school music lessons, and the SES and urbanicity weren't included. So that's just what it's showing us there. So what's the story here? The story is that if we look at the relationship between music lessons and math test scores alone, it looks to be like a significant, music lessons seems to be a significant predictor. Whereas if we add socioeconomic status and urbanicity into the model in addition to music lessons, this is no longer as important of a predictor, and instead socioeconomic status seems to explain the bulk of the story. And if we were to compare these two models, we can say statistically that Model 2 is a significantly better fit than Model 1 in that it explains 13% more variance, and the difference between the variance explained in Model 1 and Model 2 is significant. One more point of note here, one of the main differences again between simple linear regression and multiple linear regression is the interpretation of the beta coefficients. So in multiple regression, remember, we interpret each beta coefficient as the change in the outcome given a 1-unit change in the associated predictor while holding all the other variables constant. So for example, we would say if we hold constant, or in rougher language, not exactly accurate, but colloquial language, control for student socioeconomic status and urbanicity, the effect of music lessons on math achievement is only 1.71 points. And so that's how you would interpret a particular coefficient with respect to others in a multiple linear regression model. We say that when adjusting for or when holding constant other variables, this is the value we'd have. The other thing that is interesting to note now that we have multiple predictors in the model are the standardized coefficient betas. And so these standardized coefficient betas can allow us to compare the effects of these predictors to each other, even though they're on different scales. For example, the socioeconomic status measure is on a different scale than the math achievement measure and the out-of-school music lesson measure. And urbanicity is on a different scale as well. It's another nominal variable. But if we look down the coefficient betas here, we can see very clearly that the SES is a larger effect than out-of-school music lessons. So the take-home point here is that with standardized coefficient betas, you can readily compare the magnitude of one coefficient to the other without worrying about whether one predictor is in a scale that ranges from 0 to 100 or a scale that ranges from 0 to 1 or is just a nominal dummy variable. So that is basically how to run a multiple linear regression in SPSS. And in addition, we looked at a hierarchical linear regression application where we tested one model and then tested a more sophisticated or complicated model and then ran a statistical test, this change statistic here, to determine whether the more sophisticated or complex model was a better fit to the data than the simpler model. So, thank you very much.